So today we have a nice and special episode about Einstein and how he predicted high-end sound. Believe it or not, he already knew what high-end audio is or what the future of high-end audio will be, because at his time he really lived through the very beginnings of audio technology. Vacuum tube was invented during his lifetime, and the first radio broadcasts were made while he was young, in his 20s, and he was an avid musician. So he played violin and piano because his mother was a pianist and taught Einstein from early age on to play both violin and piano. And reputedly he was a very acclaimed performer, and there was a physician who said that there are many musicians with better technique, but none who ever played with more sincerity or deeper feeling. So apparently he was really an accomplished master of the instrument, and his wife said that he always played piano and violin to get his brain working, so he used them as tools in his own life, and a lot of his creativity stemmed from music. His favorite was Mozart, and let's have another look. This was his violin, made by H Steger in 1933, and later on it was sold at an auction for over $500,000. So it's a pretty nice violin and also a nice memento of his life. But what he said is that most of the joy in my life has come to me from my violin. So, and also when you look at his life, he had a pretty deep thoughts about music and what music does to one. So with those words, let's play some music in the background, although it will be a sacrilege for Bach, for Einstein, because Einstein said that you should listen to Bach while your trap is shut. So I will be giving my speech here, so sorry Einstein, but you just have to trust me on that. So now we will be listening to a little bit of Bach organ works, coming to you from a stereo mixtape, from cassette tape, from my Nakamichi BX2, through these nice little speakers in the background, which are the AOs. I call them AO because they use Alnico oval drivers, and they are driven by my pimped up Darling amp. It used to be actually that used to be Honey Charlie's double DC Darling amp, and I will talk about it later, what I did to beef it up. So let's get back to our theme today. Is that so far there are no single metrics of speakers that would predict sound quality, and we are using frequency response. That's basically the only parameter that they provide for measuring speakers, whether it goes from 20 Hz to 20K, but that does not really tell anything about how it will sound. And if it meets like 20 Hz to 20K within 3 dB, it will tell you something, but it will just tell you how it measures, but it won't tell you how it sounds. So there was Harry Pearson. I have been mentioning his name a lot. He's the godfather of high-end audio, and once he made a remark that if you can see the cone moving, it's not high fidelity. Let me repeat that again, just for the 99% of the engineers who design speakers out there, that if you can see the cone moving, it's not high fidelity. I said that because today the big fad is high excursion drivers. So that's where the whole industry has been moving towards, to make drivers where the cone can move out more and more and more. And the rationale behind that is that if it can move out more, you can use a smaller driver to produce the same volume, to produce the same amount of bass. And you can get a tiny cube pumping out a lot of loud noise. And that's truly terrific, because now we have those sound bars that can really lighten up your TV shows or make a nightmare of it if your neighbor is cranking it up, because it's pretty shitty usually, that noise that comes out of it. Or we have our cell phones. You can listen to music on a cell phone. So that those are really miraculous things, and with low excursion drivers that would have never happened. So we got conveniences out of high excursion drivers. But as Harry Pearson noted, that's really not the road to the best sound available to mankind. So if you want to approach good sound, then do not approach it through high excursion drivers. But even though people make tremendous efforts to make high excursion drivers palatable and improve their quality, and yes, tremendous effort has been made and success is reached, but if we were to place the same amount of effort into improving low excursion drivers, the gains you reap are tenfold, hundredfold compared to wasting it on these tiny whatevers. So let's get into Einstein's prediction. I think everyone is familiar with this equation that Einstein gave us, E equals mc square, which means that the energy a moving object has equals to its mass times the square of the velocity. So let's see an example that really illuminates this situation with cars. Let's see that you have a moving vehicle and you want to stop that moving vehicle. You have this fascinating automobile and the lady is driving it at a neck braking 20 miles an hour, and she wants to brake to 0. And let's now assume that braking requires a certain amount of energy to slow down the car from 20 to 0. And now the second scenario is we have a race car hurtling at 200 miles an hour, and you want to brake it to 0. And now let's assume for simplicity's sake that they have the same mass, so we can take out mass from the equation. Maybe this Hikomet has a 700-pound lead acid battery inside, so they have the same weight and they have to brake. And if you want to brake from 10 times the speed, the energy required to stop the object is not 10 times compared to the slower moving object, but 10 times 10 times, which means 100 times. So this means, translating it to cone excursion, that if your cone moves out 15 times more, like the cone excursion is 15 times higher, good job, we have made long cone excursion. Yeah, you've seen those videos where they have those speaker drivers and that they flap around like a monkey on a tree branch, and moving like centimeters in and out. Great job, terrific. But the thing is that if you make the excursion 15 times longer, then you need 15 times 15 the force to get it moving, get it there, and the same thing to get it back. So you need over 200 times the energy to make that longer excursion at the same frequency. So let's look at a concrete example. Let's look at an Altec 515C driver, and now we'll look at both its mass and also the excursion, so how far we have to travel to make that happen, and we will compare it to a Seas midwoofer, which is a small driver, but for our sake I'm using it because it's relatively much higher excursion, and it's used in a small cabinet, and to have high volumes come out of it, it needs to have really long excursion to move the equivalent amount of air, and this driver has a tiny moving mass, 5.8 grams. So relatively it's like moving a lightweight, while for the huge Altec driver it's 58 grams, exactly 10 times the moving mass compared to that tiny driver. And to achieve 96 dB SPL at 100 Hz with both of these drivers, the Altec requires 0.26 millimeters of excursion. So it has to travel the distance of a hairline. And this Seas driver, the high excursion driver, needs 4 millimeters to travel to reach the same SPL. So the difference between them is that it needs the driver cone for that tiny driver has to move 15 times faster. So it has to travel at an extreme speed compared to the driver that has low cone excursion. So basically, while the big Altec is taking a walk in the park, the small high excursion driver has to break world record in speed running. And because of that, it has to accelerate to tremendous speed, so it means it requires tremendous power from the amplifier to accelerate it. And once it reached the end of its trajectory, the cone has to be brought backwards. So it requires tremendous control from the amplifier to move it back and break it at the precise point where it has to go further again. And that's why high excursion driver speakers require amplifiers with tremendous damping factors. So this is why damping factor now in our age is so important, because high excursion drivers demand it. They are useless without high damping factor. However, in the old age, when we used low excursion drivers, damping factor doesn't count SHIT, because you don't need to accelerate that cone to crazy speeds. It remains under the control of the amplifier, and you don't need to find gimmicks to bring it under control. So it's like a comparison of cars. If you have a personal vehicle traveling at 10-20 miles per hour, it's enough if you use your brakes to stop. But if you have a drag racer car, then your brake pedals are not enough to handle it anymore. Then you need a parachute to deploy. And the high damping factor, that's your parachute that you need to use for high excursion drivers. But it's completely useless and or I would say superfluous in the case of low excursion drivers, but that's another topic. So going back here, making all the calculations, placing in the weight of the driver cones and the speed that we need them to reach at the end of their excursion. After doing all the math for solving it for both of the drivers, the difference is that the long excursion low efficiency driver requires over 22 times the energy to create the same effect as the high efficiency driver. And when I punched in all these things into WinISD, which is a computer simulation program on how drivers behave, actually WinISD gave me a 29 times power difference between the two. So if this 515C has 1 watt input, then I need 29 watts driving power for the cells to reach the same SPL. And you see, it's even greater than what Einstein predicted, because he predicted only 22.5 times power just along from the power needs, but it's even bigger than that. And that's from two reasons. One of them is that this driver is of much lower efficiency, so the coupling to the air is not as good. So that's why we need to use even more power for it to reach the same excursion. And the second thing is that the surround they use is that I will draw it here. It's like this shape, plastic surround, and it has quite significant hysteresis losses compared to the paper surround, which is like this, like a harmonica shaped surround. So all of the losses for the tiny high excursion driver or medium or whatever size high excursion driver are quite severe and significant compared to the other one. And that's just not the only issue. There's another issue that the air turbulence they create is on a totally different scale. So imagine this smaller driver, the long excursion driver, has a 12 times smaller surface area than the high efficiency driver, and it requires 15 times longer excursion. So here I wrote it the other way around for those who are watching this presentation. So the Altec is 15 times shorter excursion and has 12 times the surface area of the CS driver. And when you punch these two together, and that gives you the differential between the PSI on the cone surface. So for that high excursion driver, you have almost 200 times greater air pressure against the cone compared to a high efficiency driver, and that results in 200 times greater air turbulence caused. So just think about that tremendous turbulence causes lots of side effects. And anyway, that's just food for thought. And the next thing I want to show you is what is another major difference between long excursion and short excursion is the magnetic properties of your driver. So when we look at the driver cone, the cross section of your driver, so the driver cone is right here, these nice things, and then here are the surrounds that fasten it to the side, and the spider it fastens it secures the neck, the throat of your cone basically, and here this is the voice coil former, the blue things, and the voice coil is wound around the former, and around here that's the magnetic structure. Here this thing, that's the magnetic structure, that's the motor of your driver, and let's use blue color. And the magnetic lines travel like this. It forms a circle here and here. So actually it's like a toroid. But now we are looking at the cross section, so we just see two magnetic lines running, or two magnetic circuits rotating in the opposite directions to each other. And what we have for this circuit is we have here, there's the voice coil, and the voice coil is moving higher or lower based on the signal. And as you see, let's go back to this blue. So the magnetic lines are strongest at the very center here of the top plate, and that's the position where your voice coil is sitting still when there is no signal. And if you apply a tiny signal to it, then it moves out from this optimal position, so it will see less of the magnetic circuit that's surrounding it. And the more your voice coil, moves out, so the higher your excursion. Let's see, we look at the high excursion when it has to travel out this far, and when it travels that far, then most of your voice coil will be leaving the magnetic gap. And now people try to combat that by making the magnetic structures larger, but even with that, if you move the position of the coil, you will move how much of the magnetic current the coil sees. So basically, the magnetism provided by your motor, that's what is the backing. So that's like a floor for your cone to move from. And the more you push away from the floor, so the more the excursion is, then you change the floor. So if you go out, then the floor starts to fall out from underneath of you. And that's why the greater the cone excursion, the more imbalanced your driver will sound, because the floor will start to fluctuate, and that makes for a really nasty side effect. So let's just go back for the previous example there, where we had a hairline of travel for the Altec 515C, and our high excursion driver had to travel 4 millimeters, like 15 times more. So when you have like 4 millimeter travel, then you are in a range where the floor falling out from under you becomes a significant issue. And this was one reason why Harry Pearson noted that if you don't see the cone moving, there is no speaker distortion, because a great part of your speaker distortion comes from your voice coil leaving the optimum of the magnetic circuit. So let's just summarize what are the drawbacks of having high excursion drivers. One of them is massive air turbulence caused by the tremendous excursion. You remember my previous videos where I compared the effect of drivers with like pushing a car or punching a car. So the massive air turbulence is basically we are punching a pocket in the air in the room instead of moving the air in a controlled, civilized fashion. It just releases a lot of aggression, right? And second reason for the weaker sound of the high cone excursion drivers is much greater stress on the suspension. So the suspension has to be able to handle tremendous beating, and to such a degree where you are introducing a lot of the sonic properties of that plastic material, which is the surround. You remember that thing that looks like that blob around your driver? That's the surround material. And the higher excursion, the nastier plastic you have to make it to be able to get it strong enough to withstand those tremendous beatings of that high cone excursion. And that gives very strong plastic coloration to the sound, which you can later DSP out. Good luck with that, because that's not a harmonic distortion, it's an aperiodic anomaly, and you there's no DSP calculations to remove it, so you know, that's the thing. High excursion driver designers use DSP to correct its errors, to correct the room errors, to correct the narrow buffer errors, etc., etc. But one of the key things that would need to be corrected for them is the suspension, the problems from the surround and the spider, and you can't do that with DSP. Sorry, dead end. A third crucial drawback of high excursion is extreme demands on your amplifier. So that's why you need solid state amps that can crank out 1000 watts, 2000 watts, and so on, and have damping factor of 1000, 2000, you name it. Because if you don't have the power, you don't have your braking ability, which is the damping factor, then you cannot punch the air with that tremendously long excursion, and you cannot control your driver to make that movement. And the fourth thing is the loss of magnetic support, that you cannot do about it anything. So as you see, like, frequency extension parameter is totally secondary to the energy requirements of the loudspeakers, and as Harry Pearson said and noticed, that cone excursion is much more predictive of sound quality than any other measurement that we are doing at this point, and that's even more pronounced at low frequencies, this effect. So thank you for listening, and I hope everyone learned something. And if you liked, please like, subscribe, check out my previous videos, because they tie to this subject, will make you more informed. Thank you, bye bye.